When you hear the word robot, what comes to mind? Maybe those industrial machines that build our cars, or those slightly unsettling humanoid robots, or perhaps your trusted robotic vacuum cleaner. But nature's solutions, they look different. They are flexible, adaptable and compliant. Why does nature embrace softness, while our robots remain rigid? And what if we learned from that? Today we are going on a journey from the simple fidget toy to a walking soft robot. Soft robotics is like the yoga instructor of the robot world. Flexible, adaptable and surprisingly powerful. Let's look at some examples that might make you question everything you thought you knew about robotics. This amphibious robot uses electric motors, driving crankshafts to create undulating movements. Others, like this robotic tentacle, use pneumatics, pressurized air, to create movement. It's basically a high-tech balloon animal. And this little guy? It uses tiny explosions to jump around. And then there are robots that blur the line between machine and biology. This robotic stingray is powered by genetically modified muscle cells and is controlled by light pulses. Soft robots can handle delicate objects without sensors or complex feedback systems. They don't need to measure force to be gentle, they are gentle. Compare that to traditional robots. Yeah, they don't exactly play nice. Of course. Today we have cobots, robots designed to work safely alongside humans. But for the most part we still keep industrial robots locked in cages. So, how do we build robots that are more adaptable, more compliant, more soft? Here's something that might blow your mind. This fish is actually dead. No brain activity, no muscle control. And yet, there it is, swimming upstream like it's training for the Fish Olympics. How is this possible? The answer lies in what scientists call morphological intelligence, or, as I like to call it, the wisdom of being shaped just right. The fish's body is like nature's perfect surfboard, designed to interact with water in a way that creates movement. No muscles, no brain, just pure physics showing off. We can all agree on one thing. If you want to walk, you need legs. But walking isn't just about having legs, it's about how those legs move. If you trace the trajectory of a foot during walking, you will see it follows roughly an elliptical path. The challenge is, how do we create that motion without traditional motors or gears? You've probably seen these kinds of fidget toys before. They are made of silicone half-sphere domes. I cut out a single dome. These are known as bistable. A bistable structure is just a fancy way of saying it has two stable states. With a small push it can snap from one state to the other. What if you could use that principle to create motion? Let's jump into CAD. I designed a small bistable dome with a tiny leg-like protrusion as a first experiment. Since I wanted it to be soft, I needed to cast it in silicone. And for that, I printed a two-piece mold. Then I injected thoroughly mixed silicone. After curing, I demolded the part. And after a bit of cleaning, I was happy to discover that in fact it was bistable. Now, to actuate it, I printed a simple enclosure that lets me apply air pressure using a syringe. And interestingly, the tip of the leg doesn't just move up and down, it follows a more complex motion path. this is probably due to small variations within the dome walls. I tracked the tip of the leg using Blender, and with a little imagination it's already starting to resemble the elliptical path we need for walking. So let's refine it. I redesigned the leg, making it longer and adding a reinforcement to encourage a kind of hinge-like folding pattern. After printing the new mold, injecting some more silicone, curing and demolding the new dome leg, I was pleasantly surprised how well this worked. Once again, I tracked the path in Blender, and with the new version, the movement looks even more like a natural walking trajectory. There was just one issue. The leg kept drifting sideways slightly. Back in CAD, I tweaked the design again, elongating the structure in hopes to reduce the sideways motion. And after one more round of printing, casting and demolding, as well as producing a new enclosure, I was happy with the result. While there still is a little bit of sideways motion, I think it's good enough. But I think we can all agree that for walking you need at least 2 legs. If you build a robot with only 1 leg, it's not walking, it's jumping. Jumping is cool, but we want to walk, so let's add a 2nd leg. I printed and assembled a new version of the enclosure for 2 legs. Then I connected the syringe to the new version. Now, when I apply pressure, both legs actuate at the same time. But without any balance control, it's still not quite walking. So let's borrow a trick from robotics research. By adding a simple carousel mechanism, we limit the degree of freedom, keeping the motion controlled. I designed and printed a carousel using some bearings and a wooden dowel. At first, it was a little bit shy, but then it stood up and started moving. Time to give our robot some brains. I built a simple electrofluidic control system. Essentially, an Arduino controls a diaphragm pump and 2 solenoid valves, switching between positive and negative air pressure to actuate the legs independently. Once I connected the legs to the system and turned on the electronics, the legs seemed eager to finally start walking. Initially, I had to adjust the frequency of actuation and, most importantly, the angle of the enclosure. After a little bit of fine-tuning, it finally started to make its first steps. And then it just kept walking. There you have it. A soft, pneumatically powered walking robot, built from a bistable structure. Sometimes the smartest designs are the ones that listen to the materials themselves. So what else can we learn from being soft? Please like and share this video and subscribe to not miss our next adventure into the world of soft robotics.